Recording in progress.
We cannot hear.
She's muted.
Yeah, thank you very much for introduction. Sorry for this few seconds delay. Thank you very much for invitation and for all your efforts that you made to make this conference happen and for trying to bring me there. I'm very happy to give you this talk this way. And in my talk, I want to tell you about our radial velocity survey for planets around young stars and RVSPY. So as Jose just mentioned a few minutes ago, when we speak about discovery of planets, then we know that depending on with which technique we discover a planet, the parameters of this planet would be different. And if we would have a look on this diagram, planet mass versus time major axis, we will see very clear illustration of this. So as for today, the most numerous techniques with which we discover exoplanets would be radial velocity, transit, microlensing, and direct imaging. And in this diagram, you can see that with transit, as Jose just mentioned a few minutes ago, we can discover close planets down to very low masses of them. With radial velocity, those are blue dots in this diagram, we can discover also close and down to quite low masses planets, already up to 10 astronomical units separation from the star. And with imaging, for example, we can discover mostly only the fully array planets. So if you want not just detect new planets, but to discover planetary systems, to be able to characterize the entire architecture of the system, of the planetary system around the star, then the best would be to have a combination of, observations with all techniques, but at least a few of them would give us already much more information. And my survey, radial velocity survey around a young planet, young stars, was actually a complementary survey for another survey which was started a few years ago. So I want to tell you a little bit about search for planets around star-based imaging technique. That was a survey launched in 2015. Abbreviation would be RVSPY, imaging survey for planets around young stars. In 2013, they gained quite an amount of observational time with NATO requirement. So it's 129 during 2015 to 2019, up to the moment when NATO was not operated anymore. It was a large survey which included a contribution of 22 researchers from 6 institutes. And the main scientific goal was to observe planets, to search for planets around stars which have remnants of planetary formation, protoplanetary disks and debris disks around them. So in their sample of 130 stars are selected the ones who had these disks, and the main science goal was to discover planets at large separation outside of 10 astronomical units. And the idea of RVSPY was to complement this survey. Since Max Planck Society has his own 2-meter telescope, but I see here there's several instruments, and Pharos is one of them. So we had the chance to get quite some amount of observational time and dedicate observations for stars with disks as well. From 2018, when we started to observe our stars, we already gained over 1,000 observing hours on this telescope. Observations are ongoing, and we recently just submitted new proposals, so I expect that at least for 1 year from now, observations will be carried out. Our survey already is a result of contribution of many people, so 21 researchers from 11 institutes. But I just wanted to highlight here that it's very hard to compare actually our group comparing to RVSPY group, because for RVSPY it was also some international grants gained, and it was also people with special postdocs and PhD students positions dedicated to NACO RVSPY survey. In our case, it was only me who was ever paid for some periods for doing this research, and everyone else helped me a lot, but all motivated with scientific goals. And I believe that this is a very, very huge outcome for this, comparing to money that was spent on this project. In our sample, we down selected stars from NACO survey, but only with debris disks. This is related to the fact that young stars, that young disks have also young stars, and young stars are active, and this causes lots of complications for radial velocity survey. So that's why we have approximately 50 stars which we selected from RVSPY survey, and the rest we complemented from different literature sources to have sample of at least around 100 stars to have a larger sample for statistics. So we have debris disks, and we target planets within 5 astronomical units. Here I will just remind you this diagram and show the space, parameter space for RVSPY. This is a gray area within red line, and yellow is the area of parameter space for RVSPY. You see here two colors, and these two colors related to the fact that our survey has a structure of two parts. First part is an initial short cadence survey. This is yellow area. So the idea was to observe each star within approximately 14, well, it was a name, aim of 14 consecutive nights, one spectral per night. And after completing this survey, analyze this short cadence data and make some conclusions about parameters of stars, which we can get from spectra, and also from the short cadence radial velocity measurements, to get a conclusion about their activity. Because if a star would be very active, then it would be too challenging to find the planet in the signal, and then probably it doesn't make sense to follow it in the frame of our survey. And then second part of follow-up observations, which covers all this entire yellow region, that would be follow-up of only promising stars for which we see evidences for further companions. Here is a parameter distribution of targets which we got from the literature, so in the moment of selection of our candidates for observations. So important characteristics, expected time or temperature of these objects, which goes from M to A. Also, the main part of the sample was still from K to F3. And this is related to the fact that M stars are have too many lines which blend, and it's more complicated to detect companions within radial velocities, while stars of early spectral types are actually fast rotators, which means that they have wider spectral lines, which causes slower precision in radial velocity. That's why we try to have very few of them, just to see the general picture. For statistical reasons we kept them, but we didn't really have much hopes for the stars. So here you also can see the distances for our objects, masses, luminosities, magnitudes, and the important parameter to which I want to stop for a minute would be the age, because age goes from 10 million years to 10 gigayears, which doesn't go very well along with the title of our survey, which is radial velocity, which is young stars. And this is related to the fact that in our case, definition of use would be presence or prominence of debris disks. So that's why we admit that it's not actually that young in common understanding, but this is, like for humans. Use is never defined by the age, so it has some different characteristics. This is already parameters distribution of our targets, but this is already part of results, because this is what we determine for our sample from the spectra. The metallicities, log G, V-size, and RMS of short cadence RV data, which we got from the analysis of this short cadence array. I will not stop a lot on this part of the results. I will just invite you to the paper, which has been accepted in August this year and is already in archive. Please have a look and see more details about what our parameters and conclusions about the sample in general. Here I just want to show you a few examples of the analysis, what we've done. And in order to come to this point, I just want to briefly remind you what this sector span is, because this is a very important characteristic of the spectral line profile, to which I will refer in my coming few slides. So what happened is that when we have a spot on the star, then, and since star rotates, then we will see that on the moment when spot approaches to us, or when it goes away from us, the line of spectral line would be deformated due to the fact that the spot is located on this or another side. And it is actually very important to know that when we see radial velocity shift, is due to the fact that line is shifting to one side or another, but not to the fact that line goes through this deformation. And for this reason, it was suggested very easy check by Didier Quillon in his paper from 2001, saying that if we can very precisely measure the width of the line and determine the sector of this line, and then we compute the difference between the one on the top and one on the bottom, then we will have different values. And these values can give us a characterization of simple indicator of the symmetry of the line. And we know that if we have anti-correlation between this parameter and radial velocity, that always would be, well, that would be a very good and firm indicator for the fact that this is an activity. So in this plot, I'm showing you two example cases which we had. AGT 38949 is a star for which we saw clear anti-correlation between the sector span and radial velocity. We observed the star twice in short cadence, and it was almost clear that what we see for the star is due to the activity. We also analyzed different line indicators, but I just will not show here because actually here the sector span is more than enough. Another interesting example is CPD 722713. This star we observed in August 2018, and this star didn't have any evidence for correlation between the sector and radial velocity, and it still has the signal of approximately 4.5 days. We were very happy that we had, starting from second round of our observations, we already had a good candidate. We found archival data, which went very good with our own RVSPY data. We made the feed, and we already had, scheduled it for future observations. But then in December 2018, this data became available, and we saw that actually the signal which we see is due to the fact that star rotates, because the signal in this data, GLS power, is almost exactly the same as we saw in our radial velocity data. And this is actually the case how our first planet in our survey was killed. So one of the interesting conclusions from our survey would be radial velocity precision as a function from temperature and from V-sin. It was a very important indicator for us because we wanted to have a high precision and to know how to select candidates with a high level, with high chances to get a good precision in radial velocity. And for temperature, we see that for stars below 6,500, we would, with a high level, we almost confidently can say that precision would be in order of few tens meters per second. And for V-sin, this is also true up to 40 kilometers per second. So if V-sin is smaller than 40 kilometers per second, then most probably we will have precision good enough for detecting planets. This is the mass detection limit for future combining for the follow-up. So the important thing is here is that to see, so this is the mass and this is the temperature and the age of the stars. So important what to say that after the short cadence array, for approximately 2/3 of the sample, we still have the chances to detect planets, giant planets of course mostly, but only for approximately 25 stars, we still can detect but only brown dwarf or stellar companions. And the stellar companions is also, since we were to see the signal would be large enough, so we can also say that for stellar companions we also have a conclusion about it. By the way, in our survey we detected 7 binaries, 7 new binaries. I will not stop in my talk about this because we are only starting to prepare a new paper about it. And in our paper from this year, you can find more information about it. For the second part of my talk, I want to tell you about our first discovery in the frame of this survey, first planetary discovery. So the star name is HG 114082. It's F3 star, very young, with the age of 15 million years, at a distance of 95 parsecs. And this star has been observed with NACO, has non-detection of planet, of outside of the 10 astronomical units. But in observations with sphere, it has a very nice image of disk, which is most probably actually a radial debris swing located approximately at 28 astronomical units from the star. And from this image, we also have information of 83 degrees, which is always very helpful for observations of radial velocity. So we analyzed the data, and the MLP power of the data showed that there is for the signal. This is a data set. We also, additionally to our first observations, we found 20 data points of HARPS in the archive during the same period of our observations. And so, as you can see on this time series, we have a very high evidence for the trend in the data. We have also evidence for the fact that there is some signal in it. I will not go to the model as for now, so just coming back to the fact that MLP shown here is for the trended data already and for combined set of ferrous and HARPS data. This vertical blue line is the main, how to say this, the main specificity of this system, because among of all sample of stars which we had, we additionally analyzed the test data available for our stars, and for 91 stars out of 111, there's data already available, so one go and see if there is some signals or not. And for this star, only for this star, we had the transit event. The single transit event, which goes along quite well with the radial velocity signal. So this is result of joint feed with exostriker made by Trifonov. And so here is a placeholder plot for the radial velocity data with indication of moment of the transit. And this is a transit event, yes, a single transit event in test data. So from this feed, we found, we computed the best fit parameters of the planet. This paper already accepted, it was accepted on the last week by AMA letters. It should become public very soon, hopefully in the coming weeks. It should be already available. So our planet has 7 Jupiter masses. Radius of the planet is 1 Jupiter radian. Distance is 0.5 astronomical units and a period of approximately 110 days. So it's actually not that many planets, well, it's around 500 planets for which we have both mass and radius constrained observationally. And this plot shows all these planets. So we have here a dependence of radius versus mass of the planets from exoplanet U. And well, open circles are the ones for which we don't have we don't know the age, and age is color-coded with a color. And so this, out of approximately 500 planets for which mass and radius were constrained observationally, only 5 are, well, actually only 4 now, 5 together with our one, have mass and radius constrained observationally. These are 2 planets of around our microscope E. You can see them here, B and C. You can see them here, but since they are have much lower masses, they're actually from kind of different team of planets. And V1298, Tau B and E are here. Those are 2 planets which has age of approximately 23 million years, and these planets were known before our one. And by the absolute value, actually our planet is the youngest one comparing to these 4 other planets, because we have 50 million years, our microscope is around 2022, and V1298 is 23 million years. Also within error bars, they are kind of overlapping, so that's why we say that it's probably the youngest planet known. Importance of this planet is actually the fact that now, when we know these parameters constrained observationally, we can check the models available for planetary formation and evolution. And here, as a comparison with the planet, the exclusions, there is 2 lines from paper of Fortney 2008 for hot and cold start, and also combined model Pond and Dusty from Barafi Chandelier. And we see now that actually not only our, but all 3 planets of this mass regime are actually more compatible with the cold start, which is cost different with what we actually would expect for giant planets of this kind. And here I have come to conclusion, short summary of our survey. So the initial survey is completed. We have characterized all targets in terms of their stellar parameters and activity jitter. We have not detected a hot companion within a 10 days period, down to median mass limit of 0.5 Jupiter masses. We have confirmed 3 known binaries and discovered 7 new unknown spectral binaries with periods between 10 and 100 days. We prepared a paper about it, just some radial velocities are missing to characterize these systems. We have identified 50 stars for which we schedule further observations. 90 of those stars have evidences for planetary companion or round-Earth companion, and we have 1 discovered giant planet around HG 114082, which is probably the youngest planet with the mass and radius constraint observation. Thank you, this is it.
Thank you, Olga. Questions?
Thank you so much for the beautiful talk. If you can, this is Savis from Utah. If you, and this is a kind of a naive question I have to warn. So if you scroll back to the plot where you had the mass versus radius, can you just comment on where would habitability kind of fall within this whole spread?
Well, this question probably not to me, but to people who work more on rocky planets, because of course habitability we would not expect for giant planets, not the area which we expect to cover with our radial velocity RVSPY survey. I would be surprised if we would find some. So I would say that it should be somewhere here, and probably referred to other speakers, this question.
Other questions? Okay, if there are no more questions, so thank you, Olga. It has been a pleasure having you here.
Thank you.
I wish we'll be here, but thanks.
Yes, me too. Thank you so much.
Thanks.